Hi guys, so in this lecture we'll be discussing about replacement of hydrogen atom by deuterium atom. Okay, so deuterium is just an isotope of hydrogen only. So let's discuss that. First I write the heading: replacement of H by D. Okay, so let's look at example of it. We have something like this, and when this is put in a solution of OD minus and D2O, what will happen is we would have something like CH2 minus will take place. Why? Because this OD minus actually attacks on the acidic hydrogen of this ketone to form HOD. Sorry, uh, HOD, yes, and later the D2O will the CH2 minus will again attack on D2O to form something like CH2D. So this is the end product we find here. So in this case the acidic hydrogen was replaced by deuterium, its isotope. Okay, so what actually happens is we have let's suppose this solution of D2O, and in this D2O we have acetate also, or CS3, CS3 CO CS3, and in this if we drop OD minus, then the formation of this takes place. Okay, let's look at another examples of it. We have something like this. So this is the alpha hydrogen, this is the alpha hydrogen, or the acidic hydrogen available in this compound. So what will happen is if we react it with D2O and OD minus, so this will be the major compound formed. Okay, all the acidic hydrogens are replaced by D. Let's look at third example. We have this is H1, this is H2, this is H3, and finally this is H4. And if we pass it on a solution, and if we have a reagent OD minus and pass it on in the presence of D2O, which all acidic hydrogen will be getting replaced. So you will have something like this, that if we actually draw the resonating structure of this compound, when let's suppose it takes this alpha hydrogen, so what will happen is this OD minus will actually attack on this hydrogen atom to form HOD and a negative charge here. We have H1 here, H2 and H3 here. So then D2O will be attacked by this carbon ion to form a D here. This is one of the possible solutions. This is one of the possible positions at which the D can actually attach itself. What are the other possible? What are the other possibilities? Other possibilities are something like uh, if actually this hydrogen was attacked by OD minus, then we would have something like this, wherein we have H4 here, or let's suppose this OD minus actually attacks now this formed compound. So we would have something like this, in which we have D here, double bond O here. So in this case it attacks this is also acidic hydrogen, so we will have a negative charge here and H2 here and H3 here. So again it can attack on D2O to form something like this, double bond here, H2 and H3 here. Similarly, a negative charge OD minus can attack here on this, so we would have the final compound as this. Final compound would be D here, D here, D here, on all the acidic hydrogens available in the compound. This would be the final compound. Let us look at this example. We have something like this O here and this CH3 here. So what would be the final output of this compound of when we reacted with OD minus in presence of D2O? These are alpha acidic hydrogens. There is a acidic hydrogen here, 3 acidic hydrogens are here, 2 acidic hydrogens are here. So all these can be attacked by OD minus to form D here, CD3 here, 2D here and 2D again here. So this would be the final product. Okay, what about this compound? When it is reacting with OD minus in presence of D2O, what would be the output? This would be the output. And why? Because if you look carefully at the resonating structures, when this OD minus attacks on this oxygen OH, what will actually happen is the O will get a negative charge, and on whichever carbon atom which next gets the negative charge, I am drawing just one of the scenarios in which this double bond is actually taken over by this carbon atom. Then again the same thing can happen. This can attack on D2O to form something like D here. Okay, and then again this also has a acidic hydrogen. Again OD minus can take this acidic hydrogen, resulting in D and a negative charge here, which is again in conjugation with the pi bond here. So again D will come here, and hence we will have structure similar to or like this. Finally there can be a negative charge on O as well, so O minus can actually also attack on not here. Finally what will happen is, after we have something like this, when D is attached here and this hydrogen is acidic, then what will happen is negative charge will come on this carbon atom, and the carbon ion will actually form negative double bond here, and this double bond would be taken away by the O atom, and then minus charge would be available on this oxygen. So the final compound would be something like this. Okay, so I hope you followed how this is the final product which can be formed after the reaction of phenol with OD minus in presence of D2O. Okay, so I'm just writing one more note here that in monoketo group, keto is more stable than enol due to high bond energy of CO. So we are done with the OD minus thing. I'm just writing the note after the ending of replacement of H by D concept. Okay, so in monoketo group, keto is more stable then enol, because due to high bond energy of CO, then C. This is bond energy order. Okay, so let me draw some of the things here. That in equilibrium what actually happens is keto is keto is present 99% and enol is present only 1% in monoketo groups, and delta H of this reaction in the forward direction is 11.2 kilojoule per mole. So let's draw a chart or a graph of what the as to how the equilibrium happens and how much energy is needed for keto to convert into enol. So this is the keto group. At this is the keto group present here, and this is the enol group, and delta H of this reaction is in the forward direction is 11.2 kilojoule per mole. Okay, and if we look at the bond energy of CO is greater than bond energy of CC from this compound, that in this compound actually the bond energy of the total compound is, and for this compound the enol group is hence bond energy of this compound or the keto group is more than the bond energy of the enol counterpart. Hence it is difficult for keto group to convert into enol group. Okay, the minus sign just indicates the amount of energy released when the amount of energy the bonds actually has in this compound. Okay, so this is the amount of energy which is needed to be provided for these bonds to be broken up. Okay, so amount of energy needed here is more than amount of energy needed here due to the strong bond energy of C and O group. Hence this actually exists as 99% in equilibrium. Okay, we'll look into more such cases in the next coming lectures. So till then, good luck and goodbye.